see the hundreds of messages I just dropped. There's a whole bunch of resources in the study session planning channel. So there's a whiteboard in there if we want to use that. There's also a document. I invited a TA slash the professor to attend the study session, but I asked that they only come at the end. So this is all going to be student led. I only know as much as any of you do about any of the content on this exam. But if we have questions that we want to clarify specifically with a TA who will have more information, go ahead and post it in that doc, and then we'll refer to that when they come. And my assumption is that these things usually go about 2 hours, and then we're pretty burnt out. So the TA will come around that 2 hour mark, so then we can ask those questions. And then there's also another document in there as well for just like a study guide. So if there's resources that you have that have like a really good graphic for the calculations, I think someone posted an equation earlier that might be helpful. The study guide would be a really great place to post that. I think those are all the announcements I wanted to make about the resources that I made available. So at this point, I don't have anything specific that over. What it sounds like from some of the conversations I was seeing in some of the other channels is it might be most helpful for us to go over a practice exam, but I think that the TAs are going over the 2019 one, and that's probably the one that's most relevant. So I'm thinking maybe we should go over the 2016 one, just so that we're not overlapping too much with that. Thoughts, requests from anyone else?
Yeah, sounds good to me. I have the 2016 one pulled up here, so
Cool. Cool. Well, I'm not hearing any objections. So to keep this rolling, um, let's go ahead and pull that up. And do we want to kind of go like question by question, maybe?
yeah, it's fine.
Cool. Let's do that.
Yep. Um, but does everyone have it pulled up?
I think I'm good to go. So, ooh, and it looks like there's one of those massive questions that the professor said will definitely be on this exam. So hopefully we can get there before a 2 hour mark.
Okay, so the CPU dispatcher determines the policy for which process should be run when. Actually don't remember learning about the CPU dispatcher. I think it's probably one of the earlier lecture notes.
That's a good question. Yeah, I don't specifically remember the dispatcher.
I only have lecture 4 through current pulled up, so I have to go download the old ones.
Ooh, I'm gonna go grab those notes as well.
Yeah, if you go to lecture 2, on slide 38, like
Okay,
it talks about the dispatch mechanism.
so
I
it
think
says
that's what they're
OS
referring to.
OS runs dispatch loop.
Yeah.
Well, true, run process A for some time slice. Stop process A and save its context. Load context and address. That's the context switch. CPU dispatch returns the policy. So I don't think it determines the policy, right? It runs the process and it switches the process, but it doesn't determine the policy.
Yeah, I think
So
that's right.
I think this is false.
Yeah.
Um, So with cooperative multitasking, it is possible for a process to keep running on the CPU for as long as it chooses.
I feel like that's false, just because I don't think processes really get to make that decision. It's, I think, like the OS that maybe makes that decision.
Okay. Well, wait. You're saying so it's the process isn't going to make that decision. So like cooperative multitasking is possible process. I don't think
Wait, no,
it's
I think wouldn't that be true though? Because like the whole point of cooperative multitasking is like based on processes trusting each other and not taking over the CPU. It's like it would like theoretically be possible.
I'd second that.
okay.
I think the idea of cooperative multitasking is just what he just said. Yeah, that it's that like each process, since they trust each other, it's like they can give each other more lottery tickets, give themselves more lottery tickets, things like that.
Okay. Does anyone remember what lecture that was talked about in?
I remember it from the book,
Okay.
on the pad, the chapter on the scheduling policies.
Okay. The book on the chapter on scheduling policies. Okay. So we think that one is true. When executing the return from trap instruction, hardware restores the user's processes register from the kernel stack, changes to user mode, and jumps to a new code location. Um, and that sounds true to me. That sounds just kind of like the typical like context switch, right?
Sounds right. I just don't know if there's a gotcha in here, but yeah, it sounds right to me.
Okay.
Oh, but don't they store sometimes the processes registers not on the kernel stack in some particular situation? I forget which one. It's like in certain return from traps or in certain situations they store those registers like actually in memory. I don't know. Does anybody remember what I'm talking about here?
Yeah, yeah, like they'd store it in like physical memory.
Yeah, but then sometimes they store it on the kernel stack, which I don't really get. They're like two different circumstances.
Hmm. Yeah, I'm not finding um, like just a de facto answer on the slides. Well, I mean, I guess we can. I have the answers pulled up too. I can just look if we need to.
I was thinking we could look at the answers once we've gone through all of the like true false for part 1.
Okay, that sounds fine. So we're a little unsure on this. I mean, my initial intuition is it's true for 3. We can move to 4. When an I/O operation completes, the previously blocked process moves into the running state.
I think
True?
that's false.
False?
That's what I'm thinking too. Yeah, because I don't think there's a guarantee that it'll immediately go into running.
Okay.
I think it goes ready.
Yeah.
Okay. So false, it actually goes to ready. Number 5, the fork system call clones the calling process and overlays a new file image on the child process. Well, I'm like pretty sure it clones the calling process, right? Like it doesn't it like clone like all the like everything that's going on.
I think it does clone the parents, but I don't know about the image. I'm personally a little confused about what the image is. I don't know if that's like answered in the textbook or something.
Yeah, I don't really know about the image either. So let's see. Close.
And I don't really know what they would mean by overlays.
Yeah, I don't know. Like the first part of this, the fork system call clones the calling process sounds correct, but I really don't remember any bit about this last part.
I guess we can just send it and call it true, see what happens.
All right. A FIFA scheduler, so that's first in, first out, has a lower average turnaround time when long jobs arrive after short jobs. So what was that in? It was in lecture scheduling 3. Excuse me.
Yeah, I think it might be in virtualization CPU scheduling.
I think this is true just if you look at the turnaround time metric, since it's arrival, what is that? It's arrival time minus end time,
Yeah.
right? So if that's the case, then if the long jobs arrive first, then it's gonna drive up the mean turnaround time. But if the short jobs go first, because if they arrive like 1 second after the long jobs, they'll just sit in a queue the whole time and build up that turnaround time. But if they
I think
get
that's right.
first,
Okay. So true.
oui.
An SJF scheduler may preempt the currently running job. I forget what SJF stands for.
Shortest job
job
first.
first.
Okay.
So wait, will the SJF like actually just like stop a process and be like, sorry, we got a shorter job that just came in?
I think that'd have to be the case, right? Because like not all jobs can arrive at the same time. So if the shortest job goes first, then like if something shorter arrived, it'd have to get. Although I guess here on slide 18 of lecture 3, it says is provably optimal for minimizing average turnaround time, assuming no preemption. Hmm. And I guess the slide before that says arrivals all roughly 0 seconds. So it's assuming they all arrive at 0 time. So maybe it's false.
Wait,
I think
can
it's
you
not.
read that thing you just read on the slide again, Grizzly?
Yeah. I can actually throw it over here too for the recording. So it says here SJF is provably optimal for minimizing average turnaround time, assuming no preemption. And then on the slide before that, so that's number 18, lecture 3. On the slide before that, it has the shortest job first, and it shows arrival times. All A, B, and C are roughly at 0 seconds. So it looks like they're assuming the exact same arrival time. So I think that it doesn't have preemption.
I also think it's false. I apologize, I don't have slide numbers, but there is a slide titled preemptive scheduling, and it says FIFO and SJF are non-preemptive.
Okay, so yeah, FIFO and SJF are non-preemptive. Let's maybe we can write that in the study guide here. Let's see.
And there are a lot of acronyms floating around here.
That is something I've struggled a bit with in this class. Like classes exercise so fast. There's so many acronyms. I'm like, wait, what does that acronym mean again?
All
Like,
right. PTE, PCB, PPN.
yeah, I'm just like, fuck, man. Okay, so 7 false. 8, an SJF scheduler can suffer from the convoy effect. That was, she had some little picture about a tractor holding up traffic. So let's think about that. Shortest job first, I think, would not suffer from it, right? Since all the speedy jobs go first, so you wouldn't have a fat tractor in front slowing down the speedy jobs.
Or are they trying to trick us? And it's that because the SJF can't preempt a currently running job, that as soon as you get your big fat
Oh.
job conveyor belt, everybody's stuck behind him. I mean, I think it's a poorly worded question, but I just wonder if that might be what she's trying to get us with.
Yeah, I think you're right. That might be kind of like a trick question. So since it can't preempt, yeah, if you got like a really long job first, and then just like literally 1 second later got a short job, it's going to suffer from the convoy effect.
And
Yeah.
so the convoy is that, like horse and buggy on a highway kind of deal.
Yeah, you stuck behind the tractor, or, yeah, like the horse and buggy, which actually, if you live in Wisconsin, may have actually happened to you a few times.
Yeah. Amish country. Love it.
Okay, so I'm fine with labeling 8 as false, or I mean, no, that's true. It's true. It can suffer the convoy effect.
Great.
An RR scheduler may preempt the currently running job. So I'm going to say this is probably true based off of what MipMap said, saying that FIFO and SJF cannot preempt, but RR was not in there.
Round robin always preempts, I think, because it's just like gives you some, what do they call it? A minimum time quantum. They slice it up. Like they add up the sizes of the jobs and then divide it up so that it's all equal or something. So it's like it will always preempt a job.
Okay.
Unless what they mean by preempt is something different than just stop it before its execution is terminated. Like,
No, I think that is what it's saying. And just for anyone that was curious, when MipMap said she didn't know the slide number, it's lecture 3, slide 22, preemptive scheduling.
And then
Yeah,
the direct definition for preemptive, it looks like, is schedule differences by taking CPU away from running job.
Yep. And then it says FIFO and SJF are non-preemptive. Then in parentheses it says never deschedule a running process. So it does seem like descheduling a running process would be preempting it.
Yeah, I think 9 is true.
All right, yeah, I think 9 is true as well.
And then what STCF?
STCF is, oh God, where'd it go? Shortest time to completion first.
Okay, we gotta start keeping like a dictionary in this class because I'm not gonna be able to remember all of these.
Right. Maybe it's something we can put on the resources. Like we can just go through and start compiling all of these. I mean, it shouldn't be that hard to just go through and compile all these quick at the end of it.
Is it open note?
I mean, I don't know. I mean, does anyone know we're using AutoLock?
Are we allowed to have a little note sheet with all these acronyms written out, something, put it on the wall?
I believe it is open note, definitely. If someone can fact check me, that would be awesome. But I think the warning that she gave is that time is going to be very, very tight. So you're not going to have a lot of time to look for notes.
So you have like
So
about a minute and a half a question if it winds up being 90 questions, right? So
Right. Just some thinking for acronyms, just to have it like I can't remember what this scheduler is if I have it written down on a cheat sheet.
Yeah. And I think if you have it on like a Google Doc, so I'll make the like study guide, or if we make like a dictionary one available, like Control F is going to take you 2 seconds. So I think that'll help a lot.
Right.
Just glancing through the exams page to see if there's anything.
I have a feeling those long problems, like the one that she did in the last lecture, is what's going to take a lot of time, so make sure to budget for that.
Okay. No, so there's only stuff on here about exam conflicts. It does say that you'll have to answer or sign an honor statement at the beginning of each exam. So it looks like you could probably do open note, like even if it's not allowed, because it doesn't seem like they're gonna know. They're just gonna rely on your honor. Okay. Anyways, we're on 10, right, in STCF, so that is a shortest time to completion first scheduler cannot cause jobs to starve, and that's where it like some shorter job keeps coming in and the longer job like constantly gets like pushed down lower to a like lower level priority, right? So I think this is false. I think it can cause it to starve. Right? Wasn't that like one of the things that she said that could happen and then
Yeah, if you had a bunch of short jobs come in, as long as it's not preempting, and it doesn't, I don't think it's a preemptive scheduler.
there is a
Well-
slide on it on avoiding starvation, but I don't see a slide just on shortest time to completion first.
I'm gonna say this is false, and I think it's because the shortest time to completion is just always gonna. If you just like, let's say you had one short job come in that's 10 seconds, right, and then you have some 100-second job come in 5 seconds later, but then every second after that you get another 10-second job in. It's always going to schedule a 10-second job, and
Yeah.
that big behemoth is always going to get cut in line. And if that's what they mean by starving, then I think that might happen. But again, it's one of those questions of like, what does she mean by starve?
I think
I think
starve. I think it just means it never gets time on the CPU.
Yeah.
Okay, then I'm gonna bet that it's false because
I think it's false as well.
Yeah, I agree.
Okay. If all jobs arrive at the same point in time, a shortest job first and a shortest time to completion first schedule will behave the same. I think that's correct. I think that's true. This sounds right.
So I guess this is where I'm a little shaky. What can we think of a circumstance in which these policies would behave differently?
Let's see. I mean, if they're all arriving at the same time, shortest job first is going to schedule jobs in time to completion in ascending order, right? So like a 1 second job, then a 2 second job, then a 3 second job.
Yeah, if they all arrive at the same time, then whichever job is the shortest will complete first, and whichever job is the longest will complete last. So I think they would behave the same.
I think
Yeah.
the situation where they behave differently is shortest time to completion first is preemptive. I found it on the slides. So if you all of a sudden in some different scenario had a really short job show up, it would preempt the current job to do this really quick job. Since
Okay.
they all arrive at the same time, it shouldn't matter.
Okay. Yeah. So I think 11's true.
So wait, does that mean our answer to 7 is wrong?
No. No, I don't think it's the difference between SJF and STCF is that STCF can preempt, SJF cannot.
Oh, okay.
Right?
Thank you.
Because
Sorry.
if STCF couldn't preempt, then it couldn't cause starvation. Yeah. So I don't think we
Nice.
conflict.
Well, wait. S, uh, STCF. Can you say that last sentence again?
So STCF is able to, if it could not preempt, then it could not cause starvation. Does that make sense?
I'm trying not to be like too big brain or think too hard about it, but I'm just imagining the circumstance where you have that big job, but the big job never starts running. It's just there's always a queue of smaller jobs. So
Yeah, right. So like if the big job was running and a shorter job came in with STCF, it would then push that bigger job to a lower priority and run the smaller job, which would be preempting.
okay, awesome. Yes, thank you for entertaining me. Awesome.
Okay.
Yes.
All right, number 12. Okay, so what we say if all jobs, 11 is true. Number 12, if all jobs have identical run lengths and a round robin schedule provides worse average turnaround time. Oh, a round robin schedule provides worse average turnaround time than a first in, first out. Let's see, where's some round robin stuff? FIFO versus round robin jobs, different length. FIFO just round robin jobs, same length. So slide 31 of lecture 3 is titled FIFO versus round robin, same job lengths.
Yeah,
When
this is
Yeah,
this
that's
is
true.
because round robin's always just going to have both of all the jobs finished near the same time, right? And that's all turnaround
Yeah.
time care.
And you'd waste time in context switches.
Yeah. So yeah, this is literally the exact question at the bottom of the slide. 33 is when is round robin worse than FIFO when jobs have the same length. So true. With an MLFQ, I don't know that one. Multi-level feedback queue scheduler. Jobs run to completion as long as there is not a higher priority job. I believe that's true, right?
I think it's false because they round robin if they're at the same level.
If they're at the same level, they round robin. Okay. Oh, if as long as jobs run to completion, so long as there's not a higher priority job. Okay, so it's saying there could be two jobs, same priority.
Like when would they not run to completion?
If there was a job with a higher priority, right? So like,
Right.
yep, then it would
So
get
it's
paused
true
for
is
the
what you're
higher
saying?
priority. I'm sorry, what?
Sorry, were you saying so? Are you arguing that this is true?
That was my initial assumption, but Map said that she thinks it's false because she pointed out there could be that they get round robined if they're at the same priority. So then they wouldn't be running to completion; they'd be getting round robined.
Sneaky Professor Andrea.
So if that's true, if they get round robined, I think that Map is right and that the number 13 is false. So
All right, that sounds like something the professor would do. So nice catch, Map. I would say it's false. Yeah.
That actually wasn't me. I don't want to take credit for someone else's ideas.
oh, sorry. I just
That's all right.
Thank you, nameless hero.
Can move this so I can see everyone's voice when we talk. There we go. So now we're on 14. With an MLFQ scheduler, while a job is waiting for IO to complete, the job remains in the ready state without changing priority.
Isn't it in a block state?
Yeah, I think that's right. Hold on, let me pull up. I was just reading about this in the textbook.
Yeah, because I mean, I guess I don't know anything about MLFQ. Oh, go ahead, Map.
I think. Hold on. Whoopsies. It says, well, it's waiting for IO. I think it goes into blocked, and the reason for that is if you go to the abstraction process section of the textbook on page 7, it looks like there is IO that's initiated, and the way that it shows it is that it goes into blocked.
Okay, so 14 is false, and it actually goes into a blocked state. All right, number 15. With lottery scheduling, Ready jobs must be sorted by the number of tickets that they hold. So in terms of lecture slides, lecture 3, slide 44 begins talking about lottery scheduling. Lottery scheduling jobs must be sorted. Higher priority means more tickets, it says for the approach. So approach is give processes lottery tickets. Whoever wins runs. Higher priority means more tickets. I think from the lecture slide here, this like very short bit makes me think that yes, it is true.
That's what I'm thinking as well. Anyone want to play devil's advocate here?
I read that section like 4 times and I didn't understand it. So I will go with what the masses say here.
Okay, so I think that's true.
Cool. I think those are all the true false.
Yeah.
Would someone mind reading off what the answers are, and we can check and then go back and discuss?
Yeah, so just like read from the answer sheet, I can do that.
Yeah.
Okay, so I didn't. Hopefully, we all remember what we chose. I didn't write down what we chose for these. So number
I wrote down
one.
from most of them.
Okay, so number 1, the CPU dispatcher determines a policy for which the process should be run. That is false. It says the dispatcher implements the mechanism, the scheduler determines the policy. So I think we got that one correct.
Yeah, that's all we said.
Number 2, with cooperative multitasking, it is possible for a process to keep running on the CPU for as long as it chooses. This is true. Cooperative multitasking relies on the process to enter the OS through a system call or another trap, e.g. a page fault. If the process avoids giving control to the OS can't switch to another process.
Perfect, we said true.
Okay. Number 3, when executing the return from trap instruction, hardware restores the user's processes registers from the kernel stack, changes to user mode, and jumps to a new code location. This is true. That is what return for trap does, is all it says. So I think we said true. I think we were a little wishy-washy on this too because of the kernel stack thing. So, but yeah, true. 4, when an I/O operation completes, the previously blocked process moves into the running state. This is false. The process could move either ready or running, so it could be one or the other. I think we said it moves specifically to the ready, so we had it correct in choosing false, but we weren't like 100% on the reasoning, so it could be either ready or run.
Yeah, we said false for that one.
The fork system call clones the process and overlays a new file image on the child process. False. Fork just clones the calling process. The process needs to call exec to overlay a new file image. Okay. So.
Perfect, we said false.
Okay. A first in, first out scheduler has a lower average turnaround time when long jobs arrive after shorter jobs compared to when short jobs arrive after long jobs. It's true. If the long job arrives after the short jobs, then they will be scheduled after the short jobs. I mean, a long job after short job reduces average turnaround time, just like what SFJ does. Okay.
We said true for that.
An SJF scheduler may preempt the currently running job. False. SJF is not preemptive. Okay. I think we got that
Perfect,
one right.
we said false.
An SJF scheduler can suffer from the convoy effect. This is true. Yeah, assume a very long job is scheduled and then shortly thereafter many short jobs arrive. Yeah, okay.
Yep.
Round robin schedule may preempt the currently running job. This is true.
Yep.
An STCF scheduler cannot cause jobs to starve. This is false. Long jobs can starve if shorter jobs keep arriving. I think we said that was, yeah. If all jobs arrive at the same point in time and shortest job first and a shortest time to completion first will behave the same. This is true. They only behave differently if jobs arrive while some jobs are already running, in which case STCF may preempt.
Solid.
If all jobs have identical run lengths, a round-robin scheduler provides worse average turnaround time than first in, first out. This is true. With round-robin, identical jobs will finish at nearly the same time at the very end, giving them the worst possible average turnaround time. With FIFA, the scheduling might seem less fair, but only one of the jobs will the worst turnaround time. I don't know, they're missing a word in the answer there, but
We said true.
with an ML FQ scheduler, jobs to run to completion as long as there's not a higher priority job. False. Multiple jobs at the same priority level will be scheduled round robin. Yep.
We actually, I think we said true for this one.
I
No,
think
we
that
said false.
yeah,
Oh.
someone else
I
chimed in
read
and,
okay.
and pointed out that they did round robin, and I think we changed.
Yeah, this is the one that I missed. So, yeah.
Okay. 14 with a ML FQ scheduler. While job is waiting for IO to complete, the job remains in the ready state without changing priority. This is false. Jobs move to the blocked state when waiting for an event to complete that does not need the CPU. Yeah.
And we definitely got that.
15 with lottery scheduling, ready jobs must be sorted by the number of tickets that they hold. False. To pick a winner of a lottery, the schedule will search for the job with that ticket, which does not require the list to be sorted, though keeping the list sorted can improve efficiency. Okay. I think.
I see. So it assigns the number of tickets to the priority of the job, but then the lottery just probabilistically, jobs with more tickets will get drawn more frequently, but they don't actually do it based on the number of tickets that they hold.
Yeah, they don't actually keep them in some sorted list. They're all just hanging out together. Okay.
So it looks like we only got 15 wrong, which is pretty awesome.
Yeah, that's pretty good.
Why don't we all take the exam together? Look at that.
I wish.
Hey, I actually found that passage about the context switches. So if you guys will just humor me for a bit. So this is page 58 of the textbook on the limited direct execution. This is on context switches. So note that there are two types of register saves and restores that happen during this protocol. This first is when the timer interrupt occurs. In this case, the user registers of the running process are implicitly saved by the hardware using the kernel stack of that process. The second is when the OS decides to switch from process A to B. In this case, the kernel registers are explicitly saved by the software, i.e. the OS, but this time into memory in the process structure of the process. So they're literally like saving it to, I think, the PCB or the address space of the process.
What was? Go ahead.
Go ahead. All right, let me just finish reading this and we'll talk about it. The latter action moves the system from running as if it had just trapped into the kernel from A to as if it had just been trapped into the kernel from B. To give you a better sense of how such a switch is enacted, look at this figure. Okay, so did any of that make any sense to anybody?
Yeah, so I'm gonna ask you to, because it does say in there the first cause. It says, the hardware, it saves it to the registers. What was the first cause?
Yeah. So the first one is a timer interrupt. So timer interrupt, not based on any kind of policy or system call made by the thing. It's just simply some atomic clock goes off and then the OS automatically seizes control.
A timer interrupt doesn't sound like a return from trap, so.
Sorry, say that again?
A timer interrupt doesn't sound like a return from trap instruction, so I guess I think the thing about this part here is that this is talking about the cause for it, right? But in question 3, we don't have the cause specifically. We just have like the resultant of the cause. That makes sense?
Kind of.
So it doesn't say how we got to the trap. It just says that we're returning from the trap. And the section you're talking about here, to me, sounds like it's saying like these circumstances result in the process state being either handled by hardware or handled by software.
Mm-hmm.
Sorry, I guess I don't think that I'm answering your question. I'm just kind of
No. What you're saying, I think, is very helpful because it's kind of hard for me to parse through the differences in these things. Because I guess what I don't know is, so when a timer interrupt happens, it passes control to the OS, which happens in kernel mode, right? When the OS is in control, we're in kernel mode, right? So necessarily, I mean, again, I could be wrong, so somebody interrupt me if I'm wrong. But if that is the case, then we are in kernel mode, which means that we have to return from the trap, right? Because you can only get into kernel mode by executing a trap. Does that sound right to anybody?
I think that's definitely one way to get to the kernel mode. It might be the only way. I'm trying to like this is more from memory for me from 354 than it is from this class right now. 354 was like 3 semesters ago.
Is kernel mode and the OS, are those like the same?
I think that the OS runs on the kernel, right? It has like the highest privileges and
I think so. I'm not sure though.
I think that the kernel is often referred to as the OS, but I think strictly speaking, the kernel is like a subset of the OS. It's the part of the OS that I think directly kind of interfaces with the hardware. And I think and I think it has all system calls available to it. But the OS takes care of other things besides running those system calls on the hardware. I think
Okay.
that the OS also like is in charge of the scheduling and the virtualization and all that. So I think it's kind of like if we had a Venn diagram, I think the kernel would be like a circle inside the OS. You know what I'm saying?
Yeah, that makes sense.
Yes, and I think someone in class asked about the relationship between kernel mode and OS, and I think the professor did say she's using them interchangeably. Definitely something we could confirm with the TA, but I think that's what she said.
No,
I
I
think
remember her saying
it seems like another way you could get to the kernel mode is with like some type of failure event, like a fault. Could also get the kernel mode, but I think that's besides the point. I think that we might just be able to take it on a given that when a trap instruction is executed, it stores the user's processes on the kernel stack. And if I'm trying to remember back to 354, and I really feel like I just got images of Scretany drawing this kernel stack a bunch, but
that. Well, I think there's a good section on it, but I don't know if it's the most useful thing for us to read together, but it's chapter 6, and this section is called Saving and Restoring Context.
okay.
So if you guys want to take a look at that, maybe we can fight about it some other time. You know.
Okay,
Hey,
should
you
we
guys
move
want
on
to
to
Next question?
move on to part 2? Yeah.
Yep.
Yeah, let's do it.
Okay, so assume you have a system with 3 processes A, B, and C and a single CPU. Assume a MLFQ scheduler. Process can be in one of 5 states: running, ready, blocked, not yet created, or terminated. Give the following cumulative timeline of process behavior. Indicate the state the specified process is in after that step, and all preceding steps have taken place. For all questions in this part, use the following options for each answer. A is running, B is ready, C is blocked, D process has not been created yet, and E process has been terminated. Oh wow, these instructions are kind of dense. So step 1, Process A is loaded into memory and begins. It is the only user-level process in the system. Which state is process A in? It says and it begins, so I'm assuming it's in the running state.
Yeah, that's what I was thinking too.
Yep.
Okay. So, step 2, process A calls fork and creates process B. Process B is scheduled. Ready state? Oh, wait, no, hang on. Okay, it's 17. Process A is in which state? So, I don't know.
I think 17 is in ready and B would be running.
So that's my thought too.
So wait,
Okay.
when a user application, user level process makes a system call, does it go blocked? That's the question.
I think maybe it does go to blocked. Right, because when you make a system call, it traps into a system call. So then, like the process is no longer running.
Yeah.
Okay, so every time we make a system call, we have to trap. Is that what I'm hearing?
I believe that, yeah, that's how it works. Because like you remember in P2, there was like that trap table we made, and like our syscalls good and syscalls like returned or whatever. I forget what they're called, but we went into the trap table and we assigned them a number, like a trap code. I think like maybe 22 and 23.
Yeah.
And so those were the trap codes, and you're trapping into those system calls. So I think process A, so 17 would be blocked, and process B, it's either ready or running. Like I think maybe it's not running because I don't know if we've returned from that trap yet, right? Maybe it's just scheduled, so it's only ready. Yeah.
Well, if it gets forked, that's funny to say. If it's forked, it's been created, right?
Yeah, it's definitely been created. I mean, like from the question itself, it says it creates process B, so it's created.
And it's not running, and it's not blocked. And
Yeah,
it's
I think
terminated.
yes, I think 17.
Does scheduled mean like the scheduler loads it though?
Yeah, I don't know.
It means they put it on the calendar, but they haven't gone on a date yet.
Okay, so we're settled. Go ahead.
Go ahead.
Okay, we're settled. 17 is blocked, right?
Yeah.
All right.
I think 18 might be running, and my argument for that is just that if we want to use the CPU as effectively and efficiently as possible, if we've stopped a different process, and as far as we know, process A is the only one that's running, I think something should be running if we're going to be stopping the previous one.
Okay.
If that makes any sense.
Well, we can put down
Also
8. Go ahead.
Yeah, I also want to point out that for step 1, it does specify that process A is loaded into memory and begins, and the same isn't true for process B. So, like, it doesn't specifically tell you that process 2 begins. So they might try to get at like differentiating between like a process being scheduled and a process actually running.
Right. If the OS actually had a brain, it might be doing what Mitmap said, but it could just, maybe it has to, as like a perfunctory step, move B into a scheduled ready state before it can give it the green light.
In that case, would 17 be running and 18 would be ready?
I don't think that 17 is running.
Blocked.
Yeah, because it calls fork, so like and creates process B. So like, I think just the fact that it calls forked, it means that it must be blocked.
Does it have to be blocked? I mean, couldn't it be ready?
Oh, it could be ready. Or wait, what did we say for that one question in the true and false, right? In the true and false, there was like, okay, when an IO operation completes, oh, it was about IO operation. Is trap IO operation? I don't think it is. Because it said that one was it could be in running or ready.
Nothing is preventing it from just picking up execution again. It's not waiting on a disk read or a main memory access or something like that.
Yeah. Okay, well, what are we just want to move on from these and kind of just be like, we don't really know exactly for these two?
Are we gonna not take the answers after each question, or are you guys just doing them after each part?
I think after each part was good.
I like that.
It says in the instructions, though, that you're assuming all of your previous answers to these steps matter for the next.
Oh, that's right. Like this is kind of like this is a one giant sequence, so they're not all like independent of each other. Okay.
Oh, okay.
Will someone do the honors? Do we want to check the answer?
Sure, I can look at the answers. So let's see here. Part 2, visualizing memory. Wait, no. This is wrong. The answers...
In part 3.
Okay,
answers
yep,
are
they're
three.
swapped. Okay, so 47 says it is A is in ready and B is in running. So 47 would be B and 48 would be A if we're going by the answer key at the top. So it's not blocked. It's not running. It's ready to be run. Okay, that makes sense. Yeah. And B is scheduled, and so we're assuming then here that like when something is scheduled, it is running.
It is running.
Okay. Okay.
So does that mean our assumption about issuing a system call puts you in a block state was wrong?
Yeah. Maybe. Yeah. Maybe so. Or like.
I guess it puts it in our ready
I think
instead of blocked.
Yeah, I think fork just puts you in ready, and like an IO call would put you in blocked.
Okay. That actually segues nice into step 3. The running process issues an IO request to the disk. So A is not running, B is running. So A is still in a ready state, I would assume, right? And B is now in a blocked state.
Well, wouldn't it immediately get put into running after B is stopped? Since the CPU doesn't waste time.
That's true. It could be, yeah. A would be running, right? Since B is now blocked. So A is running and B is blocked.
Right, because we're assuming this is an MLFQ scheduler. So, and the A is the only other user level process in the system.
What does MLFQ stand for again? God dang it. Yeah, multi-level something queue? Multi-level feedback queue. Oh my gosh. Okay.
I'm gonna make that dictionary document because I think that'll help.
Yeah, can you review what that scheduler does again, quick?
What that scheduler does here, let me see here. So slide 45 of lecture 3 is called MLFQ summary. It lists some rules. Rules 1 through 5. Rule 1, if priority A is greater than priority B, A runs. Rule 2, if priority A is equal to priority B, A and B run in round robin. Rule 3, start at top priority. Rule 4, when job uses whole slice demote, that's in parentheses gaming, so it was like talking about like trying to game it where you always like save 1 second of that thing. I can't remember exactly what the thing is. Rule 5, periodically raise priority of job if not scheduled. I'm sorry, 1 second. I think someone's knocking at my door. I'll be right back.
Well, I never saw, did she assign this or like lecture about MLFQ at all? Because I like tried to read all the things. Huh?
I know she talked about it in lecture. There was like this stuff with like the boosting.
Yeah, lecture 3 covered MLFQ. I'm sorry if that's not the topic we were on, but
it looks like lecture 3. Look for the slide that says multi-level feedback queue, and then after that she starts talking about it. Sorry, I don't have slide numbers.
That's fine. It looks like MLFQ starts on slide 34 and ends on slide 45 with a summary.
I guess at like a high level, does the type of scheduler matter for these questions, or like
I think it would.
stuff?
I think it would matter. Otherwise, like if it didn't matter, they wouldn't say in the instructions at the top, assume an MLFQ scheduler. Okay, so we're on 3, and we're thinking that A goes to running, and B is now in a blocked. Correct?
We're at 3 here.
For 19
Yeah.
and 20.
So
I
we're
agree.
thinking A is running, B is blocked. Answer says that A is, running and B is blocked. So yeah,
Woo.
correct.
Right, and if we would have just looked at the next question, we would have known that one process has to be running. So the running process calls for
Yes.
versus A.
And creates process C. C is not yet scheduled. So that means that A is still in running, B is still in blocked, and C is in ready? Or no, it's not even scheduled yet. Was there not? No, so it is created. So maybe A is running, B is blocked, C is ready.
I agree with that.
Yeah?
Say that
Running
again?
block ready.
Running blocked ready. Answer key says running blocked ready. So yep, correct.
Oh,
Woo!
Step 5, the time slice of the running process expires. Process C is scheduled. So then we're going to be process A is ready, B is still blocked, and C is running.
Yep.
but we're
All right.
assuming that it's still out for IO.
We're assuming what?
The B is still out for IO.
Yeah. I don't think anything.
That previously issued IO request.
Yeah, so it's still waiting in step 5. So we're thinking A ready, B blocked, C running.
Yeah.
Answer key says ready, blocked, running. So that is correct. Step 6, the previously issued IO request completes. The process that issued that IO request is scheduled. So I think before we said that if something is scheduled, it is running. So A is in ready, B is in running, and C is in ready.
I think so, yeah.
Yeah.
C
So
scheduled.
wait, what?
Wait, no, I was saying C. I think C is ready.
Yeah, so we're doing ready, running, ready, right?
Okay, yeah. My bad.
And answer key says ready, running, ready. Okay,
Woohoo!
cool. That one wasn't so bad. It'd be nice to maybe do one of these with a different scheduler at some point too. Maybe if we have time at the end, we can look at another exam and see if there's one with a different scheduler.
For sure.
Okay, moving on to part 3. Job scheduling 2 points. Assume a workload with the following characteristic. A arrived first, B arrived second, C arrived last. CPU burst time in seconds. That means the total job completion, right? Does that sound correct?
So, I guess.
Okay. So A is the longest job, and then C and then B would be the shortest job. Given a FIFO scheduler, what is the turnaround time of job B? So turnaround time is time to completion minus arrival time, right?
Yeah.
12
That would
seconds.
be 12 seconds? No, it will be... Okay, what I said can't be right, because if it was time to completion minus arrival time, it would be... Oh no, 6 minus 2, right? So it'd be 4 seconds? So arrival time is 2, completion time would be 6, correct?
Yeah.
Well, if it's a first in, first out, job A got there and had to run for 8 seconds.
Oh, that's right. So
Yeah.
It runs for 6 seconds, right, before B can start.
As
FIFO does
non-
allow interrupt.
yeah, FIFO doesn't preempt. So job A is going to complete. So it's
You'll
turnaround
complete it, so the turnaround is
10 seconds. I think that's correct. B is 10 seconds. We want to look at the answers right away with this one, or we want to do everything and come back?
I think we should do everything and come back for this one because I don't think the answers are dependent on one another.
Okay, so we're saying 30, we're saying 10 seconds. 31.
How do we get to 10 again?
So arrival time is 2 seconds. So we have and completion time for for A is 8 seconds plus completion time for B. So 8 seconds plus 4 seconds would mean it completes at 12 seconds minus its arrival time of 2 seconds.
Okay. Okay. Makes sense.
That makes sense? Okay. Given a FIFO scheduler, what is the average turnaround time of these 3 jobs? So we know that, or we're assuming that B is 10 seconds. I think that A is 8 seconds, and then 12 plus 7 is 19, minus 5 is 14. So we have 8 plus 10 plus 14 is 32. 32 divided by 3 is, it's either what, 10 and 1/3 or 10 and 2/3? 10 and 1/3, right? Or is it?
10
I
2/3.
10 and 2/3. Okay.
2/3.
Okay, so we're thinking that 31 is C. 10 and 2/3.
Maybe a good idea to have a calculator for the exam.
Yeah, for sure.
Yep.
Given a shortest job first scheduler, what is the turnaround time of job C? So since shortest job first does not preempt, it should just be the same, right? So, which would be, what was it, 14 seconds, right? 19 minus 5, 14 seconds, I think. Yeah.
Hold on, I just want to make sure that I'm understanding this. So job A would run, and then would job B interrupt job A, or job A would
In
finish
neither
and then
No, there's no.
in neither FIFO or SJF is there preempting, so every job finishes as it arrives.
sweet.
So I think 32 is still just 14 seconds.
Which schedulers preempt and which ones don't again?
I'm sorry, what?
Which schedulers do the preemption? Which ones?
Round robin does.
Does STCF do? Yeah.
I think we kind of settled on everything except for FIFO and SJF preempt.
Okay.
Is that
So-
something we would want to confirm with the TA, or do we feel pretty confident about that?
I think it would be fine to confirm. It's an easy question for TA to answer. All right, so moving on to 33. Given a shortest job first scheduler, what is the average turnaround time of the 3 jobs? I think it's the same, isn't it? So it'd be,
The answers aren't the same.
yeah. So the E would be none of the above, right? So
Oh yeah, I think so.
because I still think it's 10 and 2/3 seconds. So 33 is E. 34, given a round robin scheduler, what is the turnaround time of job B? So it would interrupt because it's shorter than job A, and then it'd interrupt at 2 seconds. So then it'd be 2 minus, or it'd be 6 minus 4, which is, wait.
So I think
right?
each time the job arrives, we have to recalculate the time slice that we give to each one. You
I
know
think
what
the
I'm
time
saying?
slice is always 1 second, but yeah, like where they line up, I think it's recalculated.
Yeah.
And since
Like
C
the
would
time
arrive
slice-
before B completes, but it's not shorter, so I think it would be faster. So turnaround time, is the turnaround time just 4 seconds on it? So it'd be none of the above? Or is the turnaround time when it completes? So it'd be, gosh, I don't know. I gotta go look at what turnaround time is for round robin.
It's going to be the
guess
same
it
with
arrives.
you just have to do the calculation. Sorry, go ahead.
Say so like it arrives at 2, and then we have to figure out where it ends up, right?
It arrives at 2 and it'd end at 6, right?
I think so, because job C would take longer. So I think job B would probably run through completion.
Yeah, so
Well, it's round robin. It just shares equally for regardless.
Oh, it
of
shares
the
equally. How many seconds does each thing get then? It would share equally, so,
One
well,
time slice.
Can we consider a time slice to be a second? Is that just the easiest way to think about it? Or
well, I don't know. If they're shared equally, I'd think like then A would have 6 left and B would have 4, so that's
It says the time slice is 1 second at the top of the question.
oh, if needed to assume a time slice 1 second. Yep, it does. I did not see that. So then it would interleave with A 1 each time, so it'd be
C is going to arrive during its execution too, which makes it more complicated.
oh, so that'd be another second. So then we'd have 4 for A, 4 for B, and 1 for C for a total of 9, right? So 9 seconds. B.
But once C arrives, does C like get immediately thrown into the round robin, or does it go like in the back of the round robin, so to say?
I think you're right.
Could we
So
hop on the whiteboard real quick and see if we can sketch this out?
Yeah.
sure. Someone want to take initiative with that?
I can try to do it. Where is the whiteboard? Session planning, it looks like.
It's like, yeah, it's in session plan. I think it was the first link, the awwapp.com.
Right.
So what, like, A is running for 2.
Can you see my screen?
Well, everyone can see the op thing. I don't know. It says that might be the only one in here though. Maybe I went to the wrong link. Hang on.
Hold on, let me try sharing a different one. I might have done it incorrectly.
I can see the stream.
Say Wings, maybe if you click invite and then you can paste that link since you've already started.
Oh.
Yeah, good call.
I don't know. I guess I can't, like, I go to the link and then like it reverts to having this number. Oh, join shared whiteboard. Okay, there we go.
There we go.
I think I'm joining.
So like I think we'd have like I don't know. I was just gonna like go by time slice and try to see what would be running when. Do I need to share my screen still, or can you all just are you all able to see the whiteboard? Like,
Oh no, I can
mine's
hear you.
mine's still loading, but you can just go ahead. Someone want to share the link again for me? Mine's not. Oh, here it is. Shared. Oh, I see it. I see it. We're good. Wouldn't B need to be moved over here since A runs for 2 seconds before B arrives?
Yeah, we should move B.
There we go. I got it. And then A, 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 and how long was A? It was like 1, 2, 3, 4, 5, 6. C arrives at 5 though, doesn't it?
yeah, C arrives at 5.
Yep.
we ever figure out when C arrives, does it get scheduled first, or does it?
I don't know.
Do
It
you
It's
allow
says
for 2
question.
more cycles of A and B first?
I think that it would just. I think it'd just get thrown in with the round robin, but not positive.
I wonder if there's somewhere in the notes that makes it more clear.
Because I don't know. It says if you don't know runtime of each job, round robin gives short jobs a chance to run and finish fast. But we do know
So
the
it takes
runtime
this,
of each job.
so it puts a shorter job.
Let's see if there's something else on round robin scheduler. Alternate ready process for fixed time slice. It is preemptive. Short jobs will finish after fewer time slices. Short jobs will finish sooner than long jobs. I think that it shares them evenly.
Mm-hmm.
So then it would be A, B, C, A, B, C,
Like
A,
C shows up at 5.
5.
C is there?
C. Let me get this flip. Green.
Yeah. Nice.
C.
I really feel like I missed out doing algorithms with this.
Yeah, this was really nice when we were studying for algos.
Who all was in algos last semester?
I was.
I had it with Dieter.
Is that correct?
I was.
I was.
Did anybody have Genie Kai?
Yep.
Yep.
A, B. And A was how many seconds? A was 7 seconds.
I think it was 8.
Yeah.
A is 8 seconds. So we got 1, 2, 3, 4, 5, 6. And C was
C is
5 seconds. B is 4 seconds. 1, 2, 3, 4. So this B doesn't exist. Neither does this B.
Yeah.
So A, B, C. So this would make it seem like B is finished at 10 seconds, it looks like. And then to get the turnaround time, we take the time it arrives minus the time it finishes, right?
Isn't B finished at 11 because it goes?
Yeah, it's finished at 11 seconds, I think. So then it would be arrival time, so 11 minus 2, which is 9.
Yep.
Okay, so 9 seconds. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. So these we don't need, I don't think. Oh wait, whoops. I did one too many. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5. So I don't think we need these
nothing.
ones. 2, 3. No, I got it.
Yeah. No, I think we need those. Well, we don't need them for this question.
2, 3, 4. I think this is correct here. Yeah, this seems
There are
correct.
professors who used to do that.
I think
Oh, wait.
C runs for 7 seconds.
It does run for 7 seconds, so there we go. This is correct then. So we think that it's 9 seconds for 34. 34 is 9 seconds.
What was the question?
Given a round robin scheduler, what is the turnaround time of job B, which would be the time it ends, which we're saying is 11 seconds, and then the minus the time it started, which was at 2 seconds.
Yep.
Cool. So.
But yeah, I mean, I guess it does, but that does kind of like matter with how, like, they're getting scheduled, or like how like the round robin order, I guess, because like, Like if this C was instead at the back of this thing, and then A and B were ahead, then B would be ending here like a second earlier instead. Like if when C shows up, if it goes A, B, and then throws C in at 7, instead of 5, then we'd have A, B, C, A, B, B would be here.
Then we'd also have to move around where B goes, right? Because then A would be 3 seconds. So I think that we're correct with that. Like it gets to go right when it arrives.
Yeah.
Okay.
That seems right. That would be a good question for the TA though. Also.
Yeah. All right. So just want to go with 9 seconds for 34 then, and move on to 35. So 35, given a shortest time to completion first scheduler, what is the average turnaround time of the 3 jobs? So that would be that B would show up and complete entirely at A. So the turnaround time would be 7 minus 2, which is 5. So it's 5 for B. And then, oh wait, no, yeah, because
it's the shortest job, it just gets to run until it's done.
Well, yeah, but it arrives at second 2, and then it goes for 4 seconds. So B, it would finish at 6, right? Finish at the 6th second, so it'd be 6 minus 2, which is 4.
Yep.
And then
I think A would run to completion, because it's at that point it has 6 seconds remaining, or 6 first times remaining, and C has 7.
Okay.
So then A would run for another 6 seconds after B is done, up to 12. So I guess A would be 12 seconds. I'm not sure if I'm doing that right, but then C would show up then at start at 12 and go to 19. I don't think there's an average.
Yeah, I think you're right that A would then go next. So then it would finish at it has 6 left to go, so it would finish at 12. So 12 minus wait.
I think it's an idiot. So
Is it 12 minus 0?
I think so.
So it's 12. And then C would then start at 12 and run for 5 seconds. So it'd go to
7 seconds.
17, which would be 5 seconds. Or no, because it arrived at 5 seconds. So it'd be 12. Right? 1, 2, 3, 4. It finishes at 18 seconds. And then it arrived at, when does it say it arrives?
Well, it arrived at 5, but it didn't start until 12 once A was done. And so then it ends at 7 seconds later at 19, but it has a total time of 14.
Okay. So then we got, what is it? 12 plus 4 plus 14, which is 30.
30. Yep.
Divided by 3 is 10, so 10 seconds.
Yep.
That is A, so A for 35.
Yep.
Okay, 36. Assume a shortest time to completion first scheduler for the original workload with jobs A, B, and C. Assume a new job D requiring 5 seconds of CPU time arrives at some time T. For which arrival times of T would D preempt the job running at that time? Oh man, this is confusing me. Which arrival times of T would D preempt the job? So, golly. It has 5 seconds, so A runs for 8 seconds, but then it would be tied, right? Or no, does A runs? Yeah, A runs for 8 seconds, so 3 seconds it would be tied. Would then it go or no?
Ties are, I believe, broken by whatever's currently running, since context, which is cost time.
So A would keep running, so 3 seconds is not accurate. At 5 seconds, B would be running, correct? Yeah, at 5 seconds, B would be running, so it would not preempt it. And then at 8 seconds, we decided that A would be running and it would not preempt it. So is it none of these?
It might at 13 seconds. How long is left in C at 13 seconds?
C
He
is
runs from 19, so I
so there'd be 6 seconds for C left at 13 seconds. So D 13 seconds because it'd be 1 second shorter.
Yeah.
Yeah, Humble Seeker, we can definitely try to do this again tomorrow. I think I definitely want to do some more studying in the morning, so maybe we can do like afternoon, evening, but I'll post something after this session to try to figure that out.
Cool.
Okay, awesome. Thanks everybody. This has been really useful. I got to run, but I'll talk to whoever's available tomorrow morning.
Oh,
right.
just one
Hey,
quick question for you, Humble. You are the admin of the server, right?
Yeah.
Did you mod the TA?
I did not.
He asked to be modded so he could delete any types of posts that would encroach on academic misconduct.
Yeah.
Do you want his username real quick?
No, I was hoping not to give him more authority over the thing. I mean, not that have we had a problem with academic dishonesty so far?
I don't as far as he says, no. But
I mean, that's true. You don't have to do anything.
Yeah, I'm a little reticent to do it. I mean, I think as soon as we get one violation, I will have no problem doing it. But as long as he doesn't bring it up again, I'm not going to do it. Obviously, yeah, I guess. I don't know. Is there any reason for me to be hesitant, or am I just being kind of?
I don't think. So far, he seems to have been acting in like rather good faith and been very helpful. I don't think he's gonna. Like, I guess I don't know what mods are capable of doing. Like, I don't know if he could literally just shut down the entire server on us or something, but.
Yeah. Right. Well, yeah, I guess if it becomes a problem, I'll make him a mod. I don't know, unless you guys have very strong feelings about it, then
No, I don't have strong feelings about it either way.
Yeah. Oh, that sounds good.
Yeah.
I just thought I'd bring it to your
Okay.
attention.
No, yeah, I saw it and I just pretended I didn't.
Okay, fair enough.
One other request real quick. I was just wondering, since there are a whole bunch of documents that we've been dropping today, would it be possible to get access to pin those so that people can find them more easily in the future?
Yeah, I have no problem making any one of you guys mods. I'm just more thinking about taking the control away from the students, as it were.
Sure.
So
or maybe later, if you want to make a role that just has like some basic terms for like pinning and stuff like that.
Yeah,
You don't need to.
I can figure that. Okay, great. Yeah, so I'll make a role for deputies. Excellent.
All right.
Awesome, class. Thank you.
All right. Good luck.
You too.
Okay, so we were on 35, and we're saying average turnaround time was 10 seconds, if I remember correctly. So let's move on to 36.
I think you went on to 36.
Oh no,
then.
yeah, 30. Yeah, okay, we were on 36, and we were saying 13 seconds was a time at which D could preempt a job running, which would be C. Yes, okay. So 37. I'm sorry, what?
And it wouldn't do more than one of the above. It wouldn't do 8.
No, I don't think it would. Okay, so 37. Assume a shortest time to completion first scheduler for the original workload with jobs A, B, and C. Assume new job E arrives at time 8.5 seconds. What is the longest that its CPU burst could be to preempt the job that was running at 8.5 seconds? So at 8.5 seconds, let's look back at this app. From 8 to 9, we have C running, right? And so at this point, A has 1, 2, 3, 4 left. C has, I guess, 4.5 left, and B has 1 left. So, what is the longest so it has to be 4 seconds, right? Is the longest could be because C has 4.5 left, and it has to preempt the job that is running at that exact time. So I think 4.
I think C has 5 left.
Oh, does C have 5 left? Did I miscount? Yeah, I keep thinking. I think I keep thinking that. So it has. Second, 1, 2, 3, 4, 5. Wait. It runs at 8.5 seconds. So it has 1, 2, 3, 4, 5.5 seconds left.
Can it preempt in the middle of a time slice?
I don't know.
I don't think so, because then I think that would destroy the purpose, like go against the purpose of a time slice.
So 1, 2, 3, 4. So it'd have to be 4 then, right? Because ties would go to the currently running process, and C would still be running. So 4 seconds.
Yep.
Okay. So 37 or 4 seconds. Answer D. Okay, that is it for that section. So we can kind of go back and look at the answers. Let's see. Okay, so that's not the same word. Number 30, given a FIFO scheduler, what is the turnaround time of job B? The answer is 10 seconds. I did not record. Yep, that's correct.
Yep.
Given a FIFO scheduler, what is the average turnaround time of the 3 jobs? The answer is C, 10 and 2/3 seconds, which I believe we answered. Given shortest job first scheduler, what is the turnaround time of job C? That should be 14 seconds.
Perfect.
Okay. Given a shortest job first scheduler, what is the average turnaround time of the 3 jobs? The answer is E, none of the above.
Perfect.
Okay. Given a round robin schedule, what is the turnaround time of job B? The answer is 9 seconds.
Awesome.
Okay. We're on given a shortest time to completion first, which is average turnaround time of the 3 jobs. It should be 10 seconds.
Yep.
Okay. Assume shortest time to completion first. D requiring 5 seconds CPU time. Yada yada yada. The answer should be 13 seconds.
Perfect.
Okay. 37. The answer should be 3 seconds.
3. Okay, so we got that one wrong.
Okay, so 3 seconds. Man. So I'll read the kind of explanation here. It says, given this schedule, shortest time to completion first schedule, A is 0 to 2. When B arrives, it preempts B. B goes from 2 to 6. A goes from 6 to 12, total of 8. C from 12 to 19. What is happening at time 8.5? A is running and has 3.5 more seconds of run time. Oh, right. Was we went off this drawing, which was still in round robin. So that's where we went wrong. This was round robin.
Ah, gotcha.
We just got lucky on the previous question.
Did we? Well, no, because I don't think we. Oh, I guess we maybe did. Yeah, we did get lucky on the previous question because we were still basing it off of a round robin diagram. So, so 37 should be C, 3 seconds. I feel like we would have gotten that if we had been looking at the correct diagram. So overall, I think our answers were pretty accurate there, and I think that if this was considering a round robin, we would have gotten that correct. So
yeah, I agree.
Okay. Moving on to part 4, virtualizing memory. Designate if the statement is true or false. The heap and stack are statically allocated portions of a process's address space. I think that's false, right? The heap. Oh no, I'm thinking the stack grows towards like the next stack frame, right? So like, is that correct?
Yeah, the heap is not statically. It's not static, right?
Because doesn't the stack and the heap grow towards each other?
Yes, I think that's correct. So like, is that saying like then the entire the entirety of both of them are a static allocation, but neither one of them are static themselves.
I think an operating system also has rules that, like, in the off chance that the heap and stack would start to overflow, that like you would have to reallocate things. So from that perspective, I think they're dynamic.
Okay, so 38 is false. They are dynamic.
Are they both dynamic? I thought somehow like only the heap was dynamic, and like the stack was statically allocated.
Yeah, I kind of felt like the stack was statically allocated, but since the heap is in here, like we're pretty certain that the heap is dynamic, but
She might have said something about a process needing slightly more stack space, it being able to get it at one point, if I'm remembering right. There's some way to allocate more in the virtual
Like what
address
S-break
space.
does.
Yeah.
okay. So in any case, we do think that 38 is false.
Yep.
39, the address space for a process contains all of physical memory. I think that's false, right?
False.
Yeah, they
That's
each
false.
get their own virtual address space, which then corresponds to some chunk, and like isn't that why we have like the bounds registers and stuff, right?
I think so, yeah.
Okay, so 39 false. 40, with dynamic relocation, the OS determines where the address space of a process is allocated in physical memory. I think that's true.
Is dynamic relocation that like process of going through the virtual address space and then taking it to the physical?
Yeah, like the OS kind of like takes the virtual address space and then like goes and reallocates it to, or like not reallocates, like relocates it to the physical space.
Yeah, I think so.
Dynamic relocation. Yeah, I think that 40 is true.
Okay, I can get on board with that.
41, two different address spaces that do not share any pages must contain valid VPNs from one another. Two address
Different
spaces.
valid VPN.
Two different. Wait, what?
You're good. I thought you just dropped the word different. You're good.
Okay, two different address spaces that do not share any pages must contain different valid VPNs from one another. I don't know. I think that's false, right? Because like they could have the same virtual page numbers, but they would be different in the physical. So I think this is false. I think they can have the same valid virtual page numbers. What?
We have the same. Can two things have the same virtual thing but still different physical?
I think that's correct. So I think this would be false because they can have the same virtual, like because each process has its own like virtual thing. That's like the whole thing, right? It tricks each process into thinking that it has like access to all of the physical memory itself, when in reality it doesn't.
Yeah, that's right.
Okay, so 41 is false.
Side note: is that like what the offset is for?
I think so, right? Like man.
Like each process is like given like a certain offset where it's sort of living.
And like the actual physical space?
Yeah, or is it like a whole thing with page tables and other stuff? I don't know.
I think that might not be relevant to this question specifically, but they do have that. But I think that 41 is false. 42, an MMU converts physical addresses to logical addresses for user level processes. I forget what MMU stands for. Is that
Memory Management Unit. Does anyone know what lecture that was mentioned in?
I'm thinking it is in lecture 4. There's 11 instances of MMU in the lecture slides. So let's see. Dynamic relocation requires hardware support. Memory managed unit. What'd you call it? Memory manage. What? Oh, memory
management
management unit. Okay, MMU dynamically changes process address at every memory reference. Process generates logical or virtual addresses in their address space. So that makes it seem like it goes from. Wait, generates
I
logical.
don't think it's true then.
Memory hardware uses physical or real addresses. So let's see. OS can control the MMU. Memory feeds a physical address to the MMU, and MMU takes a logical address and gives it to the CPU. User level processes. I think this is false. I think that it.
So it's backwards in the question, which is why it's false.
Yeah, I think it is backwards. I think that it takes the physical address and gives a logical address to the user process, and it's S. Oh no, that is what it says here.
So the process gives it a logical address.
The process, yeah. So the process gives the MMU a logical address.
I mean,
So
is it a one-way thing, or does it just sort of like contain some algorithm that's mapping between the two?
I can copy and paste the diagram onto the whiteboard here, I think. Oh no, maybe I can. I just got a snippet here. Okay, it is on the whiteboard here. This is the diagram I was looking at. Place image. So an MMU converts physical address to logical address for user level processes. I don't know, cause like they seem bi-directional, so it seems like I could kind of do both to me, right?
I think the point is though for user level processes. So a user level process is only ever going to feed it
A logical address. So yeah, I think that's the correct reading of the question, is so that
It's kind of evilly worded.
yeah, if for was from, or if physical and logical were on like swapped sides on the word to, I think it would be true, but I think this is false then. It converts logical addresses to physical addresses for a user level process. So false. Okay. So 42 false. 43, with segmentation, the address space for each process must be allocated contiguously in physical memory. Let's see. Maybe this is going into lecture 5.
For segmentation, under slide disadvantages of segmentation, it says each segment allocated contiguously in physical memory.
So that's a disadvantage. It's allocated. Yeah, and like later we talked about how to get rid of that. So
yeah, so I think it's true.
It's true. Okay.
But isn't it the individual like segments have to be allocated contiguously, but not the address space? That's the whole point of segmentation, to have separate segments.
Oh, that's a good point.
Okay. Wait. So with segmentation, the address space of each process must be allocated contiguously. Okay. So each segment does not have to be allocated contiguously itself, but I don't know.
The whole process's address space doesn't have to be contiguous, but a segment itself can be contiguous. That address space can be across several segments.
Okay, so
Good catch.
I think.
So this is false. Yeah, no.
It's true. I don't know. I thought or my understanding of it was that the segments can be the segments themselves don't have to be continuous. They can kind of like bounce around, but then within each segment it's still continuous. But maybe that understanding is wrong.
Yes, I'm thinking that a process can take advantage of several segments, but those segments themselves need to be contiguous.
So true.
So false, because
So
the
false.
again, it's the wording, I think.
Okay.
The address space of each process must be allocated contiguously. So not the segments. The segments themselves must be contiguous, but the whole address space of the process consists of segments.
Okay. Okay. That makes
So
sense.
False.
False. 44. With segmentation, each segment has its own base and its own bounds. I think that's true.
So I think so.
Yeah. Okay. With pure segmentation and no other support, fetching and executing an instruction that performs a store from register to memory will involve exactly 4 memory references. Oh, golly, I don't know.
I think that's false, but I'm trying to find evidence for that.
Forms a store from a register.
Sorry, is this number 45?
Number 45, yes.
Hey guys, by the way, I'm Robert, the TA. If you guys have any questions for me, just let me know.
The TA should have. I think we do have at least one question. We got 2 questions we've written down so far. We have, how do we know if a process becomes ready versus blocked? So I think that was relating to like, what was that about? Was that about
It was like when stuff is scheduled, does it immediately start running, or is it just put into a ready state?
Another one of the easier ones to answer here, it's like more clearly defined questions, are first in, first out, and shortest job first the only non-preemptive schedulers? So like, are all other schedulers we've talked about preemptive?
Oh yeah, that's a good question. What's the whole list of schedulers?
So I think what
like,
we've
what
learned
are the
about,
other options?
I think what we've learned about is FIFO, SJF, MFQT, gosh, all these acronyms are kind of messing with me. Multi-queue priority, MQPT. Let me pull up the scheduling.
Oh, multi-feedback.
Yes. Round robin and lottery. Yes, those are the ones we learned about. So FIFO, SJF,
Right.
round
Okay,
robin, MLFQ, and lottery.
I don't know how lottery works, but yeah, the other ones are definitely preemptive.
Okay. So this one is likely true with potentially the exception of lottery. Gosh, I wish we would have maybe jotted down a bit more about the how do we know if a process is ready versus blocked. Did that have to do with the trap maybe?
Like if a second process starts, how do we know if the first one goes into ready versus block? And I think it also came up with, there was something about if there's IO, I think we decided that it goes into blocked, but are there other situations that it may go into ready, and how do we know?
Oh yeah, okay. So I mean, basically a process is in ready by default. and it's only in blocked if it block. Basically, it has to block itself. So if it does like a system call that's blocking, then it will be blocked. Yeah. So IO would be a good example of a way to block a process. Another thing would be like if it's waiting on a semaphore or something like that. But yeah, usually it's going to be ready. Well,
Okay.
I guess I shouldn't say that. Yeah, it's ready unless it blocked for some good reason.
So not all system calls blocked or put it in a block state is what you're saying. Only some do.
Yeah, because I think some system calls will just like they don't require or they don't trigger a context switch. So I'm thinking like if you write, if you do like a printf, that's using the write system call under the hood, but that's just going to, it'll switch to the kernel, do the stuff, and then since it can do that quickly, it'll switch back to the process. I don't think there's a reason for it to.
So yeah, it doesn't waiting on
and,
anything.
Like, switch to a new process.
Okay, yeah. So like the printf would call the write system call, but it's not actually blocked in terms of like waiting on an IO input. It just context switches, does the write, and context switches back.
Exactly. I mean, yeah, like there's always the possibility when you do a system call that you'll end up getting unscheduled, like if you've used too much of your time or something. But you would still be ready. You'd just be put back into the ready queue.
Okay. I think those are the only two questions that we've had so far. So
there was also something that came up when we were working on the whiteboard, but I didn't quite understand the question, so I didn't write it down.
oh
Does
yes, I
anyone recall
remember.
what that was?
I do remember. So when we're looking at like different types of scheduling options, and I think we were looking specifically at round robin in this case. Let's say like for the example, let's say like A is running for like 2 seconds and then B shows up. Does B just get like slid right in and immediately start at time mark of 2 seconds, or does it wait like another like tick, right? Like it shows up at 2, but A still was like, oh, I'm still going in, and then it gets scheduled at 3, or would it just get like slotted right in at time mark 2?
Okay, I see. Yeah, it seems like it would get scheduled right in.
Okay.
It wouldn't have to wait. That should be specified though, because that's kind of like an implementation detail.
Okay. So for our purposes, unless like stated otherwise, it's like a round robin scheduler. The time mark that it shows up at would be the time mark that it starts at.
Yes, but I mean, you could say, what if it came in at time like 1.5 and the time slice is a whole unit? Then you would probably say, okay, it'd probably wait till time slice 2.
So
yeah.
So it has to be it'd be scheduled at the next available time slice. So if it came in at the beginning of a time slice, it would be scheduled. If it came in like halfway, it'd wait till the next available time slice.
I believe so. Seems really unlikely to get a question about that on the exam.
Okay.
I guess like specifically, like how do we know the order that the round robin puts stuff in? So if there's like 3 processes, A, B, and C, does it run them in A, B, and C, or like run them in A, C, B, or B, A, C?
Oh yeah, that was another question we had. Does it take it doesn't like give credence to like the shorter job, right? It just like gives them all equal, and whatever order they were going is like the order that starts.
Exactly. Yeah, round robin doesn't care. If there's an order, you should be given the order.
Okay. Okay. I don't know. Did anyone else have any other questions?
I think those were all the ones that I picked up on.
Okay.
Awesome. Do you guys want me to stick around in case you have other ones, or?
I don't know. I think it looks like we're about halfway through the exam, so I don't know. Like we've already been at it for 2 hours. I'm sure you probably don't want to hang out for 2 hours here, but.
Okay. Do you have my email? You can like ping me if you want me to stop back in and like. I don't know.
Ping you here in the Discord or email you?
How about email?
Okay.
If that's okay.
Yeah, I
Yeah,
mean,
that
like
works.
your name's just Rob. I'm sure we can find the email off based off of that. So
Cool. Okay. See you guys.
thanks, man.
See ya. Thank you so much for coming.
All right. So I think we're on to part, or no, we're still on part 4, right? Yeah, we're on question
We're
40,
question 46.
46. Wait, no.
We can answer for 45.
I don't think we answered 45 yet.
Whoops, sorry. Yep.
So we're still looking for more memory references on fetch.
So for that, I don't know if this is the right place to be looking, but I'm looking at lecture memory virtualization, segmentation, and paging. And there's a slide called physical memory accesses, and it looks like there are 6 memory calls, maybe, or no, there's 5 of them. And I think this is the example that we had without any assistance. So I don't think it's 4. I think it's supposed to be 5.
Physical memory accesses.
Does it say like what the memory accesses are for? Like, is there a way to remember this other than just like every memory thing has 5 references?
So I think you're looking at slide 21. It has like the top left has what's called like
move,
assembly
add, move.
instructions. Yep. And then on the right, yeah, fetch, load, fetch.
Oh, I'm seeing fetch, exec, fetch, exec,
Oh yeah,
fetch,
yep.
exec.
Fetch, exec, fetch, fetch, exec. Yes, it does seem like 5, because like number 4 doesn't have anything. Although when it says 4 memory references, does that mean like so it accesses 5900 twice? Would that only count as one memory reference, or would that still
I think it counts as 2 because even though you're accessing the same location, you're hitting it twice.
Okay. So we're saying false.
That's what I'd propose.
Okay, so it's actually 5. We're gonna say false. 46. The number of virtual pages can be different than the number of physical pages. I feel like that's probably true.
I think it's true, but does anyone have any evidence of that?
Let's see.
Are there like physical pages? I thought it was just like the physical address space and the content of a page was only existent in the virtual space. I could be wrong though.
Okay, well, so on slide 29 of lecture 5, titled Paging, it says idea, divide address spaces and physical memory into fixed same-sized pages. So that would make me think that there are actually physical pages.
I agree. Then the question remains, is there an equal number of pages in both virtual and physical memory?
Yeah, so my intuition is that is that they can be different. That you don't need same page sizes. So the page size needs to be the same. Maybe that's true then, because if they're the same size, wouldn't they also be the same number?
I mean, hopefully.
Could you have less virtual pages if you have unallocated space? You just haven't created a page. There are a set number in physical memory, but maybe in your virtual memory space you cannot have.
Okay, it sounds like we're kind of iffy on this one. So unless anyone else has other ideas, maybe let's make a guess and then hopefully the answer expands on it a little more.
Sure. I'm gonna guess that it's true.
So I'm agreeing with true. I'm thinking that there could be page tables that are yet to be allocated, or pages that are yet to be allocated in the virtual space. So there could be less.
Okay. 47. If 10 bits are used in a virtual address to designate an offset within a page, each page must be exactly 1 kilobyte. Let's see. 10 bits are used in a virtual designate offset within a page.
No. I think the page can be a different size even if its offset is at a certain point.
Okay.
Then wouldn't you have inaccessible memory in your page though?
Yeah.
So what is 2 to the 10? Is 2 to the 10 1024? Yeah.
That's a kilobyte, yeah.
So are we saying true then?
My intuition would be true.
Okay, true. 48. If a physical address is 28 bits and each page is 4 kilobytes, the top 14 bits exactly designate the physical page number. Physical address is 28 bits. Let me get out my calculator so I can. 2 to the 28th is, oh wow, divide that by 10. I don't know, these numbers are so large.
Well, so like a kilobyte is 10 bits, and so then
so
4 more bits will get you like to 4 kilobytes. I think.
2 to the 12 is 4K.
Yeah.
So 2 to the 14 would be 16K.
So here we're looking at 28 minus 14. Or wait, you said how many is 4 kilobytes? Is that 2 to the 16?
2 to the 12.
2 to the 12? So then we would be looking at 28 minus 12, which should be 16. So then this would be false because it should be 16.
I think so, yeah. I'm actually not really sure what the function of the top n bits for. Like, do the top n bits designate a physical page number, or is it for something else?
I think that's correct. Here, let me add slide pulled up here. Let's see.
Based on slide 30, I think that's right, because you have the PPN and then you have the offset.
Yep, it looks like the only things that are like the only 2 things that are segmented in there are the physical page number and the page offset. So yeah, it should be false and it should be 16. Or wait, no. Was it 12? I forgot the numbers we threw out there.
Yeah, 4K is 12, so.
Okay, so it's 28 minus 12, so it should be 16. So 48 is false. 49, a virtual address is 8 bits, and each page is 32 bytes. Then each address space can contain up to 8 pages. If a virtual address is 8 bits and each page is 32 bytes, then each address space contain up to 8 pages. I do not know. How many bits are required for 32 bytes? 35 5 bits for 32 bytes, because what, right? There's 8 bits in a, or there's 8 bits in a byte, right?
Yeah.
Yeah, I think that's confusing me too. So 32 bytes, you can represent that with. Well, I know you can get to 32 with 2 to the 5.
Okay, I think that's right. So we got.
But you use only 5. Does 5 bits give you 32 bytes, or does it only give you like you have to have a factor of 8 in there somewhere?
I don't know. I think everything she was dealing with was always like 2 to the power something or something to the log base 2 of the something. So I think 2 to the 5th seems right. So we got 8 minus 5 would be
3 bits.
Yeah,
3
and
bits.
when you're assuming that a page table entry is
And then that gives us the bits for a page, the bits required for a virtual page number.
yeah, so it'd be 2 to the 3rd left, which is 8. So 8 pages.
8 pages, so true.
I think so. I think it's true.
Okay. 49 is true. That might be something to write down about, is how to like a formula for fill this in later. Okay. 50, given a constant number of bits in a virtual address, the size of a linear page table decreases with larger pages. I think there was a slide about this. Wasn't this like one of the quizzes we had? Was there like some pyramid diagram she drew? I forget.
Oh, yes, I think there is a diagram. That sounds really familiar. Give me a second.
There's a table on address format that has page size. Let's see. So, given a constant number of bits in a virtual address is a constant number of bits. Okay. The size of a linear page table decreases with larger pages. I think this would be true.
What's the like? I'm confused with the differences between a page and a page table.
So pages exist within a page table, right? So like if we have like a page table with like, and a page table can have only so many number of like only like can only be so big, right? So like a page table has like a certain size in bytes or kilobytes or whatever, right? And then each page is also a size, so like it can only fit like a certain number of pages. So
Like, does the page table stay the same, even like larger pages, but with like less pages in the same table?
Right, the size of the linear page table decreases with larger pages. So you need more bits to be able to reference all the memory in each individual page. So the page table shrinks since you have less pages.
Ah, okay.
Okay.
Think
So
that's good.
this is true?
So the page tables, yeah. So the page table size is a function of the number of pages.
If you look at slide 8 from lecture 6, there she drew a little diagram.
Okay. Lecture 6, slide 8, you said?
Yep.
Which one?
Lecture 6, slide 8, disadvantages of paging. Let's see. Wait. Lecture 6, slide 8, disadvantages of paging, or is that not the title of that slide?
Yeah, disadvantages of paging. It was something she drew that I happened to copy. I'm thinking I'm reading it right.
Okay, I did not copy what she drew there.
Okay. Let's see if I can. If I can screenshot this and put it in the Discord. Forgive my horrible handwriting, but
Session planning? Yes, okay. Why not make pages very small?
Right. So the more pages you have, the smaller offset you have.
right.
And so then there'd be the less number of pages you could have?
Right. So like as your offset grows, that means that like as the page size itself grows, the less you can have for a fixed number of bits in your virtual address.
Oh, right. Yeah, okay, that makes sense.
Okay. So 50 is true. 51, given a fixed page size, the size of a... Wait. No, that's what we just did. Wait, no, it's not. Given a fixed page size, the size of a linear page table decreases with smaller address space. I mean, with smaller address space, there's just less amounts of pages you can have, right?
Yeah, I think that makes sense.
So then it'd be a smaller page table. So when I say smaller page table, it just means the number of pages on the page table, not like the size and like memory of the page table, right? So 51 true?
Yeah, I think so.
Okay. 52, given a 20-bit virtual address and 1 kilobyte pages, each linear page table will consume 1 kilobyte. So I think this is the thing that I posted. So it's virtual add 2 to the virtual address bits, which is 20, minus log base 2.
So you have 2 to the
1024.
10.
I think this one is true.
Isn't it? But isn't the linear page table? Isn't it multiplied by the size of each page table entry, which is
That's true. Times
4 bytes.
PT
So wouldn't it
size.
be 4 kilobytes?
Oh yeah. Wait, how do we know that it's 4 bytes?
It says at the very beginning of the exam, you just assume that a page table entry is 4 bytes. I think it was 4 up here. Yeah.
Yes,
Page table
right.
entry requires 4 bytes.
Yeah, because you'd have 10 bits.
Yeah.
Kilobyte of what?
Yeah, I think you guys are correct. So I think that 52 would be false.
When you do like the 20-bit virtual address divided by like the 10 bits of the pages, right?
So yeah, like if you look at the note resources on the Discord, I have a formula for this, and so like if you follow that formula, the page table size in bytes is 4096, which yeah is 4 kilobytes, not 1 kilobyte.
Okay.
So I think this is false. It would be 4 kilobytes.
Great.
Okay. 53, compared to peer segmentation, a linear page table doubles the number of memory references, assuming no TLB. I really don't remember peer segmentation at all.
Well, peer segmentation is just base and bounds, and those are stored in registers, so you don't count them as memory accesses.
Okay.
So, assuming no TLB, is that accurate?
Assuming no TLB.
Doubles the number of memory references.
I have no idea for this one.
I mean, it certainly increases if you're looking up memory.
Okay.
In your page table, in your linear page table. I don't know, doubled.
What is peer segmentation again?
I do not know. I do not have an answer for that.
I don't know if I can give a succinct, complete answer, but it is when you have segments of memory and each virtual address, or each like virtual address space has a base register associated with it, and you use that base with a bounds to figure out your physical address.
Okay.
So we're saying this is true?
I would say true, but I'm not certain of the number of.
Okay, like so we think that it does make the number of memory references bigger, but we're not certain that it's double.
Sorry, I didn't understand.
Okay, so we'll just go with true on 53. 54, a workload that sequentially accesses data has good temporal locality. That's false. That's sequential, or what's it called? Is it called central?
Spatial locality.
Spatial locality. That's it. Yeah, right. Because it's like doing it sequentially, which means they're right next to each other. So this is false. It should be spatial locality.
Yep.
55, on a TLB miss, a new page in physical memory is allocated by the OS.
No.
No, I didn't think of anything. I was pretty sure that page table entries are all like kind of handled by what the MMU, right? So it's not the OS doing anything.
Yeah, if you have a TLB miss, it just means you have to go out to your region of memory that your page table points at to find your entry in physical memory.
Okay.
Versus
So
just getting it from the TLB.
Okay, so 55 is false. 56, a page fault occurs if the valid bit is clear equal to 0 and a ETE needed for memory access. Is that true?
Let me look up page fault notes.
Yeah, we definitely went over this in a recent lecture. I just don't remember exactly which one.
Yeah. So lecture 7. I don't even have lecture 7 loaded up here. Page faults in lecture 7. Lecture 8. Okay. That's not. think that it's not the valid bit, but the other one.
The dirty bit?
No, wasn't there? Is that what it's called? The dirty bit?
You're right, dirty bit. Yeah, because the dirty bit gets set when what's in memory is different from what is on the disk.
And when is the valid bit set? Okay, wait, no, there's permission, read write, there's the valid, the present, and the dirty. So, okay, extend page tables, extra bits, present and dirty. What's, you know, let me put the present bit. What does present bit do? The present bit is set if the page is in memory. I don't see anything like that specifically mentions page fault.
I'm looking at the most recent lecture, so I think it's lecture 8, the swapping one, and there is a slide called Virtual Memory Mechanisms that does mention page faults. I'm just not 100%
Okay, let's see.
like how it relates to this question. And the previous slide, present bit, also mentions page fault.
Okay. Yes. Else page fault. So, okay, virtual memory mechanisms. First, it checks TLB for the virtual page number. Let's say it's if it's present, right, then it would be a hit and it would just go. Okay. Otherwise, it's a TLB miss. And then if PTA designates pages present in the pages in physical memory, else. So I think that with these two else's, I feel like the second else is below the second if. So it's a little bit. So like there's a table miss, and then if the PTA designates the page as present, then the page is in physical load TLB, but if it's not, then there's a page fault. So I think that the present bit has to be 0.
But not the valid bit?
But not the valid bit.
What is the is this the same valid bit that's in the TLB? Or is this different?
Yes.
I think it's the same one.
Okay. Right, because you wouldn't page fault on a TLB miss because of the valid bit not being set.
So we're thinking that 56 is false.
So should
Okay.
go back to this after.
57 with paging. A single physical page can be shared across 2 address spaces only if they have the same virtual page number in each address space. I think that this is wrong. I think it should be physical, right? Wait, paging a single physical page can be shared. No, they can have different virtual page numbers. There was an example where she talked about, she's like, this is how you could have like physical sharing, and they had different virtual address spaces, like page numbers. One was like page number 0, and the other one was like page number 2 or something. Let me see if I can find the slide, because I got hung up on it. I like asked her to wait in the chat, and was like, oh wait, never mind. I figured it out. Okay, it is lecture 7, slide 21, sharing, paging, and segmentation. So the process 1 has like segment 9 and segment 8 have different. Oh, wait, no, hang on. Yeah, like the segment would be the page number, right? Or no, page number is 8 bits. Oh, maybe Maybe they do need to have the same page number. I think that this is false. Like it seems to me like they could have different virtual page numbers but still point to the same physical.
That's what the slide is making it look like.
Okay, so false, they could have different virtual page numbers. Here, 58. A multi-level page table typically reduces the amount of memory needed to store page tables compared to a linear page table. Multi-level page tables starts on lecture 7, slide 24. The idea is that it creates multiple levels of page tables. Outer level page directory per process. Only allocate page tables if corresponding page is used. If it only allocates it if it uses it, that makes it seem like maybe it would reduce the memory, right? Because it's not allocated if it's not used. I think this is true, because if they're not allocated, they're not using up memory, so then it could reduce the amount of memory used.
This is for 57.
57, yeah.
Or this is 58.
Is it 58? Oh yeah, 58. I'm sorry. 58, you're correct. On the last slide of lecture 7, I've got a summary of better page tables. It says problem. Some linear page tables require too much contiguous memory. Many options for efficiency or efficiently organizing page tables. If hardware handles TLB misses, page tables must follow a specific format. Multi-level page tables using x86. No, it's not really helpful. I do think from just page 24 or slide 24 of lecture 7 that it's saying that the idea of a multi-level page table only allocates page tables of corresponding pages in use would make me believe that it does reduce the memory usage.
I would agree with that. It also does say typically, so there may be cases where it doesn't, it will be the same. But with a linear page table, you're kind of guaranteeing that so much memory is used when you could be wasting it.
Okay. So we'll do 58 true. 59, given a 2-level page table and no TLB, exactly 3 memory accesses are needed to fetch an instruction. Well, oh, okay, so lecture 7, slide 28. Problem with 2 levels. At the bottom right hand, how many extra memory accesses? 3. So I'm just going to say true.
All right.
60, in memory hierarchy, backing store is larger than the memory layer above that uses that backing store.
We learned about what a backing store is.
I don't remember backing store. Hang on though. It does look like there are 3 mentions of backing store in lecture 8. So let's see here. Hardware memory.
Lecture notes in lecture 8.
What?
Did we finish lecture 8? These notes?
I don't think we finished it completely. No. So let's see. Slide 15. It looks like the first mention: leverage memory hierarchy of machine architecture. Each layer acts as a backing store for the layer above. I think that's, maybe that's correct. Each layer acts as a backing store for the layer above. I mean, it seems correct because it's like her diagram's like a pyramid.
Yeah, I'd be inclined to put true if this were the actual exam.
Okay, well, go with true there. 61, when the dirty bit is set in a page table entry, the contents of the table entry do not match the contents in the page table. I think that's true. I think that is the definition of a dirty bit, right?
Just check.
Oh, I really have to use the restroom. I'll be right back.
I know we said he'd be right back, but on page 17 of lecture 8, says, let me find it again. In memory, when the memory contents do not match the disk contents, the dirty bit is set, not the TLB entry.
Do we define dirty bit in lecture 8 or in lecture 7?
I believe it was in lecture 8. Yeah, there's no text reference to it in lecture 7.
Cool, yeah.
Did we decide on something for that?
We have not.
Okay.
Making. Sorry, who was that?
I was just asking if we decided on something about the dirty bit. I'm trying to.
Oh, okay.
There's one mention of the dirty bit in lecture 6. Oh, there's like some notes down here. Let's see. Oh, okay. Okay. Okay, so lecture 8, slide 17, page in memory, but in-memory contents do not match those on the disk. Dirty bit would be set to 1.
So it seems like this question is incorrectly referring to the TLB contents versus what's in memory and what's on the disk.
Yeah, so this would be false then, right?
I think so.
Julio, I apologize. I do have to skedaddle because unfortunately I have to go take a COVID test. But this was super, super helpful. And if people are interested in a study sesh for tomorrow, don't forget to vote for that.
Okay, I mean, like, do we just maybe after you leave here, we finish up the last like 5 questions and we save part 5 and beyond for tomorrow?
Yeah, that sounds good.
Okay,
Yeah, stay with me too.
cool.
Sweet. Okay, good luck, and hopefully I'll talk to all of you tomorrow.
All right, later, Mips.
Thank you.
Thanks. Bye.
Okay, so 62 of a clean page and a dirty page have both been accessed recently. The page replacement algorithm should replace the clean page over the dirty page. I feel like... Okay, is the wording saying that it replaces the clean page, like writes the clean page over the dirty page, or is it saying like it should get rid of the clean page and not the dirty page? The wording on this is a little weird in my opinion. If it's saying that it should replace the dirty page with the clean page, I think that's true.
I think it's asking if it should replace the clean page instead of the dirty page.
Okay. So if it's saying that it should replace the clean page instead of the dirty page. Oh, wait, hang on. Right. Okay. I think what it's saying is it has these 2 pages loaded all ready to be accessed without like going to memory. And it's saying that like if one of them is exactly the same as what's in memory versus something that's not the same as in memory, you'd want to replace the thing that's the same as in memory, right? Because you want to preserve the changes that you've made. So it should replace the clean page because the clean page is the same as in memory. So it wouldn't matter if you get rid of it. Or my
what does it mean to have like a dirty page or a dirty bit again?
A dirty page means that like the stuff that's stored there is not the same that's in memory. So like if you like had changed something, right? And so it's no longer the same as in memory. So until it writes that to the memory spot.
Okay.
Does that make sense?
I think so. And dirty bit just tells you like if that like writing has happened yet or not.
I don't think it tells you if the writing is happened. Maybe it does. Like it just means that like whatever is currently loaded here is not the same as what's in memory. So like I think that you wouldn't want to get rid of the dirty page. You'd want to get rid of the clean page because you can still just go back and get the same contents.
Yeah.
So true?
Yep, I'm going with it.
Okay. 63, a TLB miss is usually slower to handle than a page miss. Gosh, I guess I'm kind of confused to the hierarchy of it. I think this is false, right? It's like, if you have it in the TLB, then you don't have to go look up the pages stuff. So just be, wait.
Right, because a page miss is when you'd have a page fault and you have to swap it back in from disk, which would take pages.
Okay.
So a TLB miss would just be a memory lookup versus going out to the disk.
Okay.
So that would be false.
Okay, false. 64, a different user level process should be scheduled when a page miss is being handled. I mean, I have no idea.
Might be true because it's I/O. It would be whatever it is handling this page miss. It's being blocked by the disk.
That's right. I remember someone in lecture asking if accessing the disk or clarifying that accessing the disk was actually I/O, so it would be blocked. So this is true. Okay. Least recently used replacement policy always performs as well or better than FIFO. Oh golly, I don't remember. Was this lecture 8 we started going over this stuff, or when did we start going over paging policies?
Yeah.
I remember we were doing diagrams of it, but I don't remember what lecture it was in.
I think we started like the 2nd of February, so that's what I have in my notes anyway. So
So it'd be
3?
lecture 3. No, this was scheduling policies, not replacement policies.
Oh, right.
They use the same names because we just had a yes, okay, so it's in lecture 8. Swapping policy starts on 21. And then we had a pagement replacement example. 25 was our slide 25 was our quiz. Slide 26, replacement comparisons. Okay. Add more physical memory. What happens to performance? Is that LRU, OPT, guaranteed to have fewer, same number of page faults. Let's see.
She doesn't post like the filled in versions ever, does she?
Sort of, because I made a big stink about it on like the first or second day of lecture. Like, because I don't have anything to edit the PDFs in like a quick enough way, so I asked her to like post all of them so I could go print them at once instead of driving 2 hours every day to print a lecture slide. So she posts the PowerPoint slides, which pretty closely follow her lecture PDFs, but you can go through and delete the white boxes. But sometimes there's missing information, but it's just quicker to edit because they're all one big text box and you can just click in there and type.
Okay. Right.
I think that we actually haven't gotten this far in it yet. I feel like
Yeah. Well, I also have to go get tested here before they close. So
okay. Well, we can just stop it here. We were on number 65 of section 4. I'll post that in session planning.
you can pick it up and go after answers tomorrow. At 1, it looks like.
All right, cool. We'll wrap it up here then. Catch you guys tomorrow at 1.
Thanks, everybody.